the derivative of a function, f of x, tells us how that function is changing. It tells us the extent to which a change in the input variable x produces a change in the output variable y. So, for example, let's suppose that this red line here were a, let's see, yeah, let's suppose that this red line were a supply curve. I'll throw you a curveball here. Let's say this is a supply curve for a product. I don't know, what product are we making? iPhones. Sure, why not? Got one in my pocket right now. In other words, the supply curve would mean that if I choose a amount of quantity that I would like to produce and sell, then the y-coordinate would tell me the price I would have to charge. Wait, sorry. That's not a supply curve. That's a demand curve. Let me fix that. The price that I need to charge, price that I need to sell for, in order that I sell everything that I make. So let's suppose that that's what this red curve corresponds to. And so I pick a certain amount of quantity. And I apologize that our quantity number is going to have to be negative here just in this example, but I'm just trying to get to a motivation. Right? So if I'm selling, negative 1/2. The value of this function, the y-coordinate on the graph, 1, would tell me what is the price that I need to charge in order to sell this much quantity. What the derivative is going to tell me is it's going to tell me what's going to happen if I decide to change that quantity. Or likely, what would happen if I decided to change the price? Because the quantity and the price are related together by the equation that defines this curve. If I change one of them, the other one is going to change in response. Right? If I want to sell more iPhones, what do I probably have to do with the price? It's got to go down. Right? And on this curve, you notice if I want to move to the right, if I want to sell more quantity, I need to also go down. I need to sell I need to charge less for my product. Right? And it's a generic property of any demand curve in microeconomics that they're always decreasing functions. They always go down as we go from left to right. Because generally, to sell more quantity, you do need to lower the price. Right? And the derivative captures the rate of that decline. So how much do I need to lower the price in order to sell more quantity? Because that answer looks like it's different over here than it would be over here or over here. Right? So what the derivative ends up telling us is it tells us the rate of change of the y quantity with respect to the x quantity. And on a graph, what that rate of change is interpreted as is it's interpreted as a slope. So just kind of draw in this little triangle here. The slope of this line. This line is called a tangent line, by the way. Tangent just means that it touches the curve at that one point and it goes in the same direction as the curve at that one point, right? So it just barely comes in here and kisses this point and keeps going. The slope of this tangent line is what we mean by the derivative of f, evaluated at the x value negative 1/2. And if this is a demand curve, it also has an interpretation that you're going to get deeper into later in the semester. It's the same as what's called marginal demand. The interpretation here being that it's an answer to the question to sell one more unit of quantity. How should I change the price? How must I change the price? Ugh, I'm running out of room. How do I change the price? All right. So there's both an interpretation, a graphical interpretation of what a derivative tells me. It tells me how steep. It tells me the slope of a tangent line drawn to the curve at that point. and also a motivation for why you're going to care about derivatives, especially later on in the semester as you start to get more deeply into the applications of calculus and start working on projects and things. That it tells me how a change in one variable related by a function relates to a change in the other variable. When it's price and quantity, it can tell us something like this. If I want to sell one more unit, then what do I how much do I have to drop the price that I'm selling my units by? So, long story short there is that whatever the derivative we're looking for is, it's going to be the slope of that blue line right there. And the derivative varies, on this graph at least, from one point to another point. Because if I were to go up here to this other part of the curve, let's say x equals 3, my slope is still negative, but it looks like it's a very shallow slope when x is equal to 3. So it's touching the curve at that point. On the other hand, if I rewind back here and I go to a place like negative 0.7 or negative 0.8, right, those points along the curve, we have a very steep slope. So that slope varies from place to place, and so the derivative varies from place to place. That's why the derivative is also a function of x, because for different places on the graph, we get different slopes. So let's come back to negative 1/2 over here. I want to know what is the slope of this line. Well, if I already have a graph at my disposal, I can just pick 2 points on that line, right? And then I can just find the slope of the line that joins those 2 points. So let's do that just for the refresher. I happen to have a really nice accurate graph of this line, and I can see that 2 of the points on it are negative 1/2, comma 1, and then also 0, comma 0. And since I know those 2 points are both on my line, how do I find the slope of this line? The old recipe. Yep, we find the differences in the y-coordinates. So 1 minus 0. If you like, we can decorate these with y2s and x2s and all of that wonderful stuff. y2, x2, x1, y1. Right, so you subtract the y-coordinates. 1 minus 0 is going to give me 1. And you subtract the x-coordinates, negative 1/2 minus 0. And then we just do the division. 1 over negative 1/2, that's negative 2. So because we have this nice, awesome graph, we can say what that derivative is at this point. But of course, that's not why we came today. We came today to figure out how to do that proceeding from the formula, right, without relying on a graph, because graphs aren't always as accurate as we'd like them to be. If we do it with algebra and formulas, we know that we're getting the exact right answer. So we're going to keep negative 2 on ice for a little bit while we try to figure out what's really happening here. The first observation about what's happening here is that we had written this function, 1 over 2x plus 2. We had written it in a different way, 2x plus 2 to the power minus 1. And when I look at that, I see 2 things happening. If I'm x, the first thing that's happening to me is I'm getting doubled and increased by 2. So there's that piece. I'm going to call that piece g. G of x equals 2x plus 2. And if I'm x, that's the first thing that's happening to me when this expression is getting evaluated, because it's order of operations. It's inside the parentheses. But then the next thing that's happening, after that is all done, is then the power of negative 1 is being taken. So there's another function here that's being applied to the result. It's the reciprocal function, h of x equals x to the power minus 1. And the function that we care about in this problem is built out of those 2 pieces. And the goal is to figure out how its derivative is related to the derivatives of those 2 pieces. Right? So what's the relationship between f and g? This is a relationship that you probably spent some time on in pre-calculus. What is it? How is f built out of g and h? G of x, and then the output of g of x is fed into the input of h of x. So the picture here is that if I'm x, the first thing that's happening to me is g of x is happening to me, right? And I become 2x plus 2. 2x plus 2. So the g machine turns me into 2x plus 2. But then after that, that output gets fed into another machine, the H machine. And after it gets fed into the H machine, only then do we finally get 2x plus 2 quantity raised to the minus 1. So what we have is a composition of two functions, is what we call it. And the composition of those two functions is what we call f here. So f is built out of these two pieces. First g happens, and then h happens. So if I'm x, then in my notation, the first thing that happens is g, and the second thing that happens is h. And so we end up wrapping x into these two layers of functions. G is my first layer, h is my second layer. Here's my shirt, here's my coat. Right? So we call this a composition of two functions. It's different from multiplying two functions together. It's different from adding two functions together. It's feeding the output of one function into the input of another function. We're feeding the 2x plus 2 that we get out of g into the input of the h function, which takes the reciprocal of whatever it gets. Right? And so we're decomposing this function into two pieces. So the question is, how does the derivative of the composite, f, relate to the derivatives of g and h? How do I figure out what the rate of change of this with respect to that is by understanding the rate of change of these and those? So let's go experimenting. And where I'm going to experiment is here are the graphs of the two functions g and h that we had on the previous slide. And let me change the colors so that they line up with what we had. What did I use? H was blue. G was red. Is that what I used, or was it vice versa? It was vice versa. Let me fix that. So this was red. This was blue. Okay. So if I'm x, what was the first thing happening to me again? If I'm x, the first thing happened to me was the g function. Actually, I think it was vice versa again. I think it wasn't g. Just trying to... Sorry. When x was equal to negative 1/2, the first thing that is going to see that negative 1/2 is the g function, my 2x plus 2. And so what I would do is look for x equals negative 1/2 on the g function. Here it is, negative 1/2. G is my blue graph here. And I would ask, what's the derivative of this function when x is equal to negative 1/2? And that's a derivative we know how to take. If g of x is 2x plus 2, then what is g prime of x? What did we say was the derivative of 2x plus 2? 2, regardless of the value of x. And so what I'm going to do is just sort of draw a little arrow here and say slope equals 2 at that point. Okay? So now I know, let me get my little conceptual picture back in here. I know that in my little diagram that shows me how f, g, and h are related to one another, that the rate of change associated with the g step, that rate of change is 2. Positive 2, right? And again, x turns into 2x plus 2, and then that turns into 2x plus 2 to the minus 1. H is this one. Right. Okay, so then the question is, h has to do its work after that. But when h does its work, what input is h getting? H is getting an input of whatever g spit out. And g of negative 1/2 is the y value of this point. That y value is 1. Whoops. 1. And so as far as h is concerned, h doesn't see the original input of the function g. H only sees the input that it gets, which in this example, when x is negative 1/2, 2x plus 2 is 1, and so the input we get for the h function is the input 1. So if I want to understand what the rate of change of the h part is, I need to look at x equals 1 for that rate of change on the h function. So I promise this is going somewhere. Meanwhile, the h function, h of x equals 1 over x, we know how to take its derivative. How how do I take the derivative of 1 over x?
X to the negative first.
Yeah. It's the same as x to the negative first. So when we take its derivative, what happens?
Multiply the 1 that's in front of the x
Mm-hmm.
by negative 1.
Negative 1.
Subtracting 1 from negative 1, so negative 2.
Yep. And I can take that x to the power minus 2 and bring it down here. So there's the derivative, h prime of x. And so when I plug x equals 1 into that function, what's going to happen? Negative 1 over 1 squared. It's going to be 1. Sorry, negative 1. So the slope at this point is negative 1. Now, thinking back to when we computed the derivative of f of x a while ago, right? Before we even went to this slide, what was the derivative of the f of x that we started with? We had a number we underlined. And I said, let's put this on the shelf for a minute. It was negative 2. So my question is, how could we have gotten that number out of these two numbers? What do you think? Multiply them together. That is the chain rule. And I know we took 20 minutes or so to set it up, but this is the observation for why the chain rule works. Right? It's that each function in the composite is only getting the input that it sees, but that after we've gone through multiple steps, the rates of change along these steps, all they have to do is multiply one another, and we get the rate of change of the whole thing. So the rate of change at the h step was negative 1, and then when we combine those two things together with f, the rate is the product, positive 2 times negative 1. 2 times negative 1, that's negative 2. So that's the motivation behind how this all works. And so what I need to do now then is let's bring that back to where we started this journey. Way back here. And we want to know, what does that mean about how we find the derivative of this thing? And this will be where I stop talking as soon as I get this up on the screen. So what we did is we envisioned this as a composite function. It's one function wrapped up in another. 2x plus 2 wrapped up inside of the reciprocal function, x to the power minus 1. Right? And the chain rule told us the following. It told us that the derivative of that composite function is related to the derivative of its pieces just by multiplication. So here's how it works, chain rule. That if f of x is equal to g of x wrapped up in h of x, then the derivative, f prime, is going to be the product of the two derivatives, h prime multiplied by g prime. So I always recommend writing out the chain rule if you're trying to remember it. Write it out like this, right? There's the multiplication happening right there in between the h prime and the g prime. But I've suspiciously left those parentheses empty for a minute because we have to remind ourselves what input these functions are getting. Well, g is getting the input x, right? And so that ends up going here also, g prime of x. But what input is h getting? It's getting the input g of x. And that ends up being where we need to evaluate the derivative for h, because that's the input that h sees. And now this formula here looks a little bit scary. It's just got a lot of pieces. But the important bit of it is the multiplication, first of all, right? We're just multiplying the rate of change of g by the rate of change of f. And when we do so, we just have to be careful that h prime is being evaluated at g of x, and g prime is being evaluated at x. So that if I do this chain rule up here for f of x equals 2x plus 2 to the power minus 1. The idea is first that I take the derivative of the outside function, the h. And here the outside function is the reciprocal. So here's how I think of it. And this might be what you take away from this discussion the most. How I think of it is, we need to take the derivative of something. But at this stage, it doesn't matter that that something is complicated. We're just going to kind of put a smiley face over it for a second and ask, what's the derivative of smiley face to the minus 1? What happens when you have a power of minus 1? How do you take its derivative? Yeah. Minus 1, smiley face to the minus 2. Exactly. It sounds silly, but I find this works for me. You kind of squint your eyes at what's inside those parentheses, and you just treat it like it was otherwise an x. Minus 1, smiley face to the minus 2. And that covers this first step, because then if we take the smiley face away, let's see if I can do that here. If we take the smiley face away, we realize that there was actually something underneath it, 2x plus 2. But I put the smiley face there because a lot of times people are tempted to change what's there when they take this derivative of h. Right? Resist that temptation. At the first step, it doesn't change at all. Then what? We did the first step. Now we have to multiply by something. The derivative of the smiley face. Right? The derivative of 2x plus 2. And what is the derivative of 2x plus 2? 2. So that piece goes on the outside. And that's it. That's all there is to it. I mean, we can simplify this. Minus 1 times 2. Give me a minus 2. I can take this minus 2 power and use it to move the 2x plus 2 into the denominator if we want to. That's all just algebra. This is one of those rare cases where the tricky part is the calculus. The tricky part is applying the chain rule. And the shorthand, again, is you take the derivative of the outer function without touching the inner function, and then multiply afterwards by the derivative of the inner function. Derivative of outside, leaving the inside alone. And then after that derivative happens, multiply by the derivative of the inside. So that was the full motivation for why the chain rule is what it is. Then there's the formula for it. And then there's the sort of the procedural, the mechanism, the mental shortcuts that I think of when I do the chain rule.